to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing scientific breakthroughs that are touching our lives, that are going to shape the destiny of the human race. Okay, well, without further ado, let's move on to the first listener phone call.
Hey, this is Armand from Queens. I was wondering how possible you think it is to go subatomic, like a person being able to shrink down to the subatomic level, like in the movie Ant-Man, because I really like that movie. Have a great day. I like your station a lot. It's awesome.
Well, thank you. And yeah, when I was a kid, there was a movie, The Incredible Shrinking Man, where a man shrunk himself and he had to fight off bugs and insects. And of course, these bugs were gigantic in size. And then you had Disney movies, Honey, I Shrunk the Kid. And we may ask ourselves a simple question. Is it possible that we can really shrink ourselves? And in fact, Matt Damon was recently in a movie where he downsized himself, and the cost of living dropped dramatically because his food bill, his electricity bill, his water bill was almost nothing. So is it possible to shrink things? Well, the short answer is no. Sorry about that. And why is that? Well, first of all, what are we made of? Believe it or not, we are made out of nothing. That's right, nothing. Most of our body is a pure vacuum. And if you don't believe me, we do this experiment for our physics students. We get a piece of uranium and then put a Geiger counter behind your back, behind the uranium, and the Geiger counter registers radiation as if you're not there at all, as if you're made out of nothing. Because your atoms are basically empty. That's right. Your atoms are basically empty. Now, if your atoms are basically empty, so we're basically made out of nothing between the atoms and between the electrons and neutrons, protons, then why can't we shrink us? Well, the reason is quantum mechanics. It turns out that quantum mechanics set distances, like the distance to the hydrogen atom, and they cannot be changed by any known law of physics. So sorry about that. Honey, we're not going to be able to shrink the kids anytime soon. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to throw the lines open because it's open mic. Well, the previous phone call actually raised a bunch of physics questions. He asked a question about whether or not you can shrink people, and for that matter, whether you can expand people, and what would it be like if we can somehow become Ant-Man. Well, when I was a kid, I used to love watching the movies like Them. In that movie, ants became the size of a house. They were mutated. And the question I asked myself as a kid is that possible? That an ant can become the size of a house? Or what about King Kong? Or what about the incredible 50-foot woman? These are some of the movies that I saw when I was a kid. But now I'm a physicist. And now I realize that, well, it makes for great cinema, but they're not physically possible. And in fact, the laws of physics actually change when you scale something up. For example, many people think that if an ant were the size of a house, then the ant could pick up the house. Just like ants can pick up a leaf many times bigger than its own weight. So if ants can do that, if you scale up an ant to the size of a house, then the ant would be able to pick up a house, just like in the movie Them. Well, no, it doesn't work that way. You see, if I take an animal and I double its size, so instead of being 1 foot long, it's now 2 feet long. It weighs more. How much more? It weighs 8 times more. Not just double the weight. When you scale up an animal so that it's double in size, it weighs 8 times more, not 2 times more, because you have to go by the volume. The volume we learned when we were in elementary school goes as the cube of the radius. But how much stronger is the animal by doubling its size? It's only 4 times stronger, because strength goes as the cross-sectional area of your muscles, and the cross-sectional area goes as the square of the radius. In high school, we learned that the area of a square is pi r squared, and so if you double the size of an animal, it is 8 times heavier, but only 4 times stronger. So in other words, the animal becomes weaker, proportionally speaking, as you scale it up. What am I getting to? The fact that if I take an ant and I scale it up to the size of a house, its legs will break. The ant would not be able to walk at all because the legs are spindly in size. The legs are 4 times bigger if you scale it by 2, but it weighs 8 times more. And that's why King Kong is also not possible. King Kong, instead of terrorizing New York City, its legs would break. Its legs would break as soon as it took the first step. Now, that's also the reason why figure skaters are so tiny. Have you ever met a figure skater up close? Maybe you've been to Disney on Ice or something. You realize that they are very tiny people. Why? Because the smaller you are, the stronger you get, proportionally speaking. Okay? That's why little children who are 15 years old win the gold medal in figure skating. If you're very tiny, a tiny girl, you dominate the figure skating world because you're proportionally stronger than a huge hulking guy who has all that mass, all the bones that he has to lug around, while if you're a 15-year-old girl, you fall to the floor, you just pick yourself up. Now, if you're a big hulking mass and you fall to the floor, you break your leg because your legs are not proportionally stronger. And so, in other words, King Kong is not possible. Them, that is gigantic ants, are not possible because the laws of physics are not the same when you double things in size or reduce things by half. Also, if you saw the movie Honey, I Shrunk the Kids, they shrink down to the size of an ant and they meet things like water droplets. Now, think about it for a moment. A water droplet that an ant would see looks like a hemisphere of water. That's because surface tension is also not scale invariant. Surface tension also increases when you scale things down. That's why an ant would see a drop of water as a gigantic hemisphere. And now, of course, a hemisphere of water in our world would very rapidly splash, and it would essentially be wiped out. But for a tiny ant, that's not true. For a tiny ant, a drop of water looks like a gigantic hemisphere, and if the ant were to stick its legs inside the hemisphere, it would be stuck, because surface tension is also not scale invariant. And that's why sometimes when you put a little piece of sugar in liquid form on a table, ants will come, because it's sugar, and they'll get stuck. In fact, they'll die, stuck inside the honey-like consistency, because the laws of physics are not the same when you scale things up or scale things down. So in other words, in the movie Downsizing with Matt Damon, when you downsize a human, you find all sorts of bizarre things happening when you get smaller and smaller. If you get bigger and bigger, you get weaker and weaker. Your legs will break as soon as you try to take a walk if you're the size of King Kong. However, if you are the size of an ant, then proportionally speaking, you become Ant-Man. And Ant-Man, of course, is a superhero. So if, and this is a big if you could reduce yourself in size, you would become superhuman. But, hey, you can't do it. According to the laws of quantum mechanics, the size of an atom is fixed. Sorry about that. You cannot shrink an atom no matter how hard you try. Okay, well, let's move on now to the next listener phone call.
Hi, Professor Kaku. My name is Nahreen, and I'm calling from San Jose, California. I listen to your YouTube channel and have a question for you regarding time travel. If according to the law of physics, time traveling is possible, what if we have right now people who time travel from future, like years 3000 or 4000 to our time? They should be advanced enough to figure out how to do it, and we should have met them by now. What do you think about that? Thank you so much. Bye-bye.
Okay, well, you ask a very interesting question, the very same question that was asked by my late colleague, Stephen Hawking. Stephen Hawking said that, well, maybe time travel is not possible because where are the tourists from the future? He said that the living room should be full of tourists from the future who want to take a picture of the great scientist Stephen Hawking, but he doesn't see them. So, well, maybe time travel is not possible. And one time, as a joke, he had a party. However, he didn't invite anyone to the party. He said, tomorrow I'm going to have a party. But he didn't invite anyone because he said to himself, in the future, I'm going to invite people, and they're going to have time machines, and they'll go backwards in time because they know I had a party. And so he waited for people to show up from the future. Well, nobody showed up from the future. So in other words, maybe they didn't get an invitation in the future to go backwards in time to meet Stephen Hawking. So you ask a very interesting question. Where are the future people? Well, there's several ways of analyzing this question. The simplest way is to say that time travel is not possible, but that's too easy because Einstein's equations do allow for time travel. Einstein said that time is a river, but the river of time can have whirlpools, and the river of time can fork into two rivers, in which case you can actually go backwards in time. Einstein himself realized that. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question, a very profound question that my colleague Stephen Hawking asked himself many times, and that is, where are the people from the future? If time travel is possible, maybe not today, but if time travel is possible in the future, then perhaps our descendants will have gone backwards in time to visit their illustrious ancestors, i.e. us, and they should be taking pictures of us. They should be shaking our hands. So why not time travel? Well, ever since Stephen Hawking made that comment years ago, many scientists have come up with their own private theories. One possibility is that maybe they have visited us, except after visiting us, they realize that we're a bunch of fools in the past with nothing to offer them, and they just get bored. I mean, let's say you have a time machine, and you go back to watch the dinosaurs. But after watching the dinosaurs have lunch a few million times, you get bored. I mean, they don't talk back to you. You can't have an interesting conversation with a dinosaur. It's the same old dumb dinosaur having breakfast, and you say to yourself, I'm not learning anything. This is not exciting. So maybe time travelers from the future have already visited us, but they simply said to themselves, humans are not worth visiting again. I mean, after all, if they went backwards in time and watched television and witnessed the Kardashians, they would be convinced there's no intelligent life on the earth. Nope, next planet. So that's one possibility. Another possibility is that maybe they do come back to the past, but they're invisible. Invisibility is one thing I write about in my book, The Physics of the Impossible. Yes, it is possible to make something invisible. We can't do it yet, but we can make things invisible under microwave radiation, not visible light. But the Pentagon is funding this research. So in the future, maybe we'll have time machines maybe we'll have invisibility centuries before we have time travel. And so it means that maybe we are visited. Maybe there are people taking our picture, tourists from the future, but they are invisible, and that's why we can't see them. Well, there's yet another way to resolve this paradox, and that is if you could invent a time machine by creating a wormhole, it turns out that the wormhole would connect 2 points of the present. Therefore, even if you were to separate these 2 points, you cannot go backwards in time earlier than when you built the machine. That's another possibility, and that is that, yes, you can build time machines, but you cannot go earlier than the time at which you created the time machine. That objection has been raised by several physicists. In fact, several papers I've looked at have raised that possibility that maybe time travel is possible, but not to the distant future, only to the future when you built the time machine. That's another way to get around that fact. And yet there are other ways as well. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question, a very interesting one, about time travel. And it turns out that, yes, Einstein himself realized that general relativity allows for time travel under certain circumstances. First of all, if I have a spinning object, if the universe itself is spinning, or I have a gigantic cylinder that's spinning rapidly, a spinning pole, and if you were to go around the pole or around the universe, you would go backwards in time. Another class of time travel solutions are black holes. If you could go through a black hole and stabilize it with something called negative energy, then you can open a gateway to the past and keep it stable so that you're not going to get crushed by the wormhole. That is another classification of time travel. And then the question is, well, if time travel is allowed by Einstein, then why don't we have it? Why don't we have visitors from the future? Well, let me say a few things about visitors from the future, because there are paradoxes that you encounter. Now, the mother of all paradoxes, the greatest paradox of all, was given to us by science fiction writer Robert Heinlein. And let me summarize that logic. Many, many years ago, there was a young girl that was left as a baby on the doorstep of an orphanage. The nuns picked up the baby. They didn't know where she came from, what her name was, so they called her Jane. And poor Jane grew up without knowing who her mother was or who her father was. Well, when Jane became a teenager, she became a beautiful young woman, and she got a boyfriend. But it's a sad story. She gets pregnant, and her boyfriend disappears into the darkness, never to be seen again, and she's left pregnant at the hospital. Poor Jane doesn't know who her family is, left as an orphan. Now she's pregnant, no boyfriend, and it's even worse than that. The doctors at the hospital find out that Jane is a hermaphrodite. She has both sex organs. So she's bleeding, and she has to be saved. So the doctors do an emergency operation and change Jane into Jim. Well, Jim wakes up with this huge headache, realizing, oh, my God. First, she was an orphan, left as an orphan on an orphanage steps, and then got a boyfriend, but then he dumped her, and now she's abandoned, pregnant, and then that night, somebody steals her baby girl. What a disaster. Everything went wrong. Well, poor Jim grows up to be a barroom drunk. Anytime someone challenges him and says, who are you, Jim? Are you really Jane? Where'd you come from anyway? Who's your mother, your father? Well, now, poor Jim is once again dead drunk on the bottom of a bar, and a bartender comes up to him. And a friendly bartender says, Jim, wake up. I'm really a time traveler. Come into my machine, and we will unravel the mystery of who Jane/Jim really is. And so they go back into the past, and poor Jim is left somewhere in the past. He's dazed, doesn't know where he is. But then he meets this beautiful 17-year-old girl, and it's love at first sight. But it was not meant to be. They quarrel, and Jim stomps off into the darkness. But then he finds out that his girlfriend is pregnant. And Jim says to himself, oh, my God, this happened to me when I was a young girl. I'm going to go back and make things right. So Jim goes back to the hospital, steals his own baby girl, goes back into the time machine, and then drops the baby girl off at an orphanage. And at the steps of an orphanage, the next day, the nuns find this baby girl. They don't know what to call her, so they call her Jane. And Jane grows up wondering, who's my mother? Who's my father? Well, meanwhile, Jim says to himself, I can't be a barroom drunk all my life. I got to get my act together. So Jim decides to join the Time Traveler's Corps. And he has many exploits in the annals of time. And now Jim is an old man. He's an old man now. And he says to himself, I want one last mission in time. I'm going to go backwards in time and impersonate a bartender to meet a certain barroom drunk who just got into a fist fight because someone said, who are you, Jane/Jim? Where'd you come from? Who is your mother, your father? Now, for 10 points, here's the question for you. Who is Jane's mother, father, brother, sister, and uncle? I'll give you the answer after the break. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a very interesting call from a listener who asked about time travel and what happens if you meet someone from the future. Well, as I mentioned, perhaps the greatest of all paradoxes in time travel was given to us by Robert Heinlein in a short story. And in this short story, we start off with a young baby girl called Jane, grows up in an orphanage, not knowing who her parents are. And as a teenager, she meets a handsome stranger but gets pregnant, and she's abandoned. The baby girl is born at a hospital, but someone steals her baby girl. Well, poor Jane, she's left without a family, now without her baby daughter, but the doctors realize that she's dying. They have to change Jane into Jim, a sex change operation. And Jim becomes a barroom drunk who one day finally meets a bartender, a time traveler who says, I will unravel the secret of Jane. They go backwards into the past, and Jim meets this beautiful teenage girl, and it's love at first sight, and he gets her pregnant, but he says to himself, I got to take responsibility. I cannot let history repeat itself. So he kidnaps his own baby girl and goes backwards in time once again and drops off the baby girl at an orphanage where she becomes Jane. Now, here's the question. Who is Jane's mother, father, brother, sister, daughter, aunt, uncle? Jane is a family tree unto herself. Now, can you imagine a family get-together? A family get-together and they get into a food fight, and someone says, you did this to me. No, you did that to yourself. Think about it. Is that possible? Well, if time travel is possible, you can be your own mother, your own father, your own grandfather, your own granddaughter. You can be a family tree unto yourself. So, is that physically possible? Well, yes and no. You see, Stephen Hawking finally concluded that time travel is not possible because the machine would explode when you went into the time machine. Time machines are allowed under Einstein's equations, but quantum corrections build up. And they build up to the point where the machine explodes, therefore you cannot go backwards in time. Well, I've looked at that calculation by my colleague Stephen Hawking, and I realized I think he made a mistake. He made a mistake because in quantum mechanics, if you were to go backwards in time, the timeline splits in half. Because time is constantly splitting into a multiverse of quantum universes. Therefore, when you go backwards in time to meet Jane, you meet someone else who looks like Jane, but is not really your Jane. Genetically equivalent, has the same memories as Jane, but is Jane in a different timeline. Now, I saw the movie Back to the Future Part 2, and Doc Brown goes to the blackboard and he draws a long parallel line, a long line, and says on the left is the past, on the right is the future, and here's the timeline. And then he drew a fork in the timeline. And he says that's what happens when you go backwards in time. The timeline splits and a parallel universe opens up. So in other words, instead of having one universe with many copies of Jane, no, you have many universes In each universe, there is its own copy of Jane. Now, this, of course, raises philosophical questions. It means, first of all, that if the multiverse theory is really possible, there exists another universe where you are not alive, or you turn out to be a serial killer, or you turn out to be some kind of degenerate, or you turn out to be the richest man in the world. Think about that. Waking up one day and finding out that you're in the wrong universe and that you are the richest man in the world or the deadliest serial killer of all time. I mean, you go berserk thinking about these things, and I, as a physicist, have to think about these things professionally because at the atomic level, that happens all the time. At the atomic level, yes, electrons are constantly splitting apart, and that's why we have television. That's why we have radio. That's why we have transistors. That's why we have lasers. The wonders of the modern age can all be traced back to electrons being more than one place at any given time. Now, if you get a headache thinking about these things, you're not the only one. I've been at conferences where Nobel Prize winners bump into each other, and they argue about this. 50 years after Einstein and Bohr struggled with these questions, we're still struggling with these questions. And to me, the simplest way to get around all these paradoxes is to assume that the universe splits every time a quantum decision has to be made. There are no paradoxes in time travel. If you go backwards in time, you've entered another universe. Not your own past, somebody else's past. Okay, well, let's move on now to the next listener phone call.
Hello, this is Frank in Columbus, Ohio. And my question is about Jupiter. Is it possible that at some point in the far future, Jupiter could accrete enough mass to become a brown dwarf? Currently, it's only about 1% of the mass required for a brown dwarf, but possibly as the sun becomes a red giant and starts to shed off its outer layers, could it at some point...
let me answer that question really quick. The answer is no. In order to ignite to become a star, you have to satisfy what is called Lawson's criterion. And as you pointed out yourself, Jupiter is way too small to satisfy Lawson's criterion to create another star. So our sun will be alone in our solar system. We're not going to live in a double star system, even though science fiction writers love that idea. But once again, you've been listening to Science Fantastic. Give us a call. The hotline number is 612-564-8135. And every week, you can be part of the cutting edge of science if you call 612-564-8135.